Okay, let's unpack this. What if the very tools we use to build artificial intelligence could actually be designed by AI itself?
Yeah, it's a mind-bending idea.
Imagine AI that isn't just, doing tasks, but actively creating better versions of itself, maybe even better than humans can.
It does sound wild, doesn't it?
Yeah.
And for tasks like getting computers to recognize objects in images, well, designing the neural network architecture underneath is incredibly complex.
Right.
Historically, it's relied so heavily on human creativity, deep engineering experience, and maybe a bit of guesswork too, honestly. Lots of trial and error.
We've seen these big leaps forward from human designers, right? Names people might know like Inception or ResNet.
Exactly. Those were clever, human-invented architectures, each one pushing the boundaries of what was possible at the time.
But this paper suggests maybe there's a different way entirely. Today, we're diving deep into a research paper that really stretches those boundaries. Learning Transferable Architectures for Scalable Image Recognition. It's by Barrett Zoph and colleagues at Google Brain.
And this work, it presents a really powerful new method for automating that super difficult architecture design process.
So our mission today is to walk you through the key ideas in this paper, look at their really surprising results, and figure out what this all means for the future of how we build AI, and maybe what AI itself could become. Let's jump in.
Okay, so the foundation this builds on is a concept called neural architecture search, or NAS. You might have heard of it.
Yes, right.
At its core, NAS uses reinforcement learning. Think of a controller network. It's like an AI architect.
Okay, an AI architect.
Yeah, its job is to propose different neural network designs, different blueprints.
So it just generates these potential designs?
Pretty much. It samples a potential architecture. Then a separate child network gets built according to that blueprint.
Uh-huh.
And that child network is trained on a task, let's say image classification, to see how well it does. What's its accuracy? Based on that performance, the controller gets feedback, like a reward. And over many, many tries, through this reinforcement learning loop, the controller learns which patterns and structures lead to good results. It gets better at proposing effective designs.
That makes sense, learning by trial and error, but automated. But the paper points out a big problem with doing this directly, right?
Oh, definitely.
Trying to search for an entire network architecture by training thousands, maybe tens of thousands of these child networks on a huge data set like ImageNet.
Yeah.
It sounds computationally just brutal.
It was prohibitively expensive with those earlier direct NAS methods.
Absolutely.
And that's exactly where their core innovation comes in. This is where it gets really interesting.
Okay, tell me more. What was the breakthrough?
Their big idea was realizing they didn't need to search for the whole network on the giant data set.
Ah.
Instead, they could search for a smaller, reusable building block. They call it a convolutional cell. And they could search for this block on a much smaller, more manageable data set first. Then they could take that learned cell architecture and just transfer it, reuse it, to build the bigger network for the much larger, more complex problem.
Whoa. Hold on. So figure out a good basic design on an easy problem and then just kind of copy-paste that design to build a solution for a massive, really hard problem.
Yeah.
That seems counterintuitive. How could a pattern learned for tiny 32 by 32 pixel images work well for huge, high-resolution ones? How did they make that transfer actually work?
That's the clever part of their design. They created a specific NASNet search space.
Okay.
The crucial thing about this space is how they defined it. The structure and complexity of the learned building block, the cell, is independent of the overall network's depth or the size of the input image.
Ah, okay. So the block's internal design doesn't depend on how big the final network is or how big the pictures are.
Exactly. That structural independence means a cell they learned using a small image dataset like Scifar10 could be stacked effectively to build a much deeper network, processing the large images from ImageNet.
Got it. So the final huge network isn't designed monolithically. It's built by stacking potentially many copies of these identical pre-learned cells.
Precisely. And they actually found it worked better to learn two different kinds of these reusable cells based on what they need to do in the network.
Two types.
Yeah. First, there's the normal cell. It takes a feature map as input. You can think of that as the network's internal picture representation at some stage. And it outputs a feature map of the same spatial size. Height and width stay the same.
Okay, preserves the dimensions.
Right. Then there's the reduction cell. This one also takes a feature map, but it outputs one where the height and width are reduced, usually halved. It often does this using operations with a stride of 2 inside the cell.
Okay, so that's how the network gradually shrinks the representation down. And the controller RNN's job was to figure out the best internal wiring, the architecture, inside these normal and reduction cells.
Exactly right. The controller recursively predicts the structure within a cell, block by block. For each little internal block, it makes 5 decisions.
5 steps per block.
Yep. It picks 2 previous hidden states or inputs within the cell, picks an operation for each one, like a specific type of convolution or pooling, and then it picks a way to combine the outputs of those 2 operations, like adding them together or concatenating them.
Okay.
They mention using B5 of these blocks per cell in their experiments, choosing from a set list of possible operations.
Right. And this whole search, finding the best cell structures, they did that on the CIFAR-10 dataset, the one with the tiny images.
Yes, CIFAR-10. Using that smaller data set was absolutely key for making the search feasible for speed. They trained the controller RNN using reinforcement learning, specifically an algorithm called PPO, and they spread the training work across a bunch of GPUs.
And how much faster was it? You said the old ways were brutal.
They reported it was almost 7 times faster than the previous NAS methods that they compared against. Something like 4 days on their hardware versus maybe 28 days for the older approaches. Now, hardware differs, but the estimated efficiency gain was really significant.
That's a huge difference, 4 days versus almost a month.
Definitely.
They also mentioned comparing their RL approach to just randomly picking architectures within this special search space they designed.
Yeah, they did. And interestingly, while the reinforcement learning controller did find better architectures on average, just doing random search within this well-designed NASNet space actually performed reasonably well, too.
Oh, interesting.
It suggests that maybe the design of the search space itself, that whole idea of learning these transferable cells, was perhaps just as important, maybe even more important, than the specific algorithm used to search within it. The space itself is good.
That makes sense. A well-defined problem is easier to solve. Okay, so beyond the search space and the process, they also called out a specific training technique that was vital.
Right. Scheduled drop path.
Scheduled drop path.
Yeah, it's a twist on an existing idea called drop path. Drop path is a regularization technique, basically. It helps prevent the network from overfitting to the training data by randomly dropping out connections during training.
Okay, like dropout, but for paths.
Exactly. But they found that for these NASNets, the standard drop path just didn't work very well. Their key discovery was scheduled drop path. Instead of a fixed dropout rate, they linearly increase the probability of dropping a connection path over the course of the training.
So it drops connections more aggressively as training progresses.
Precisely. And doing that dramatically improved how well the final NASNet models performed compared to using standard drop path, or even more common dropout. It seems like a small detail, but it was critical for getting the best out of these learned architectures.
Okay, so they have this clever transferable search space, an efficient search on a small data set, and crucial training tricks like scheduled drop path. Let's get to the payoff. What kind of performance did these AI design networks actually get? This is where they started breaking records, right? Starting with CIFAR-10 itself, where they did the search.
Right. On CIFAR-10, the NASNet architecture they found achieved a state-of-the-art error rate of 2.40%. That was slightly better than the best published human design models at the time.
Impressive on its own.
And the single best search run they reported hit an even lower 2.19% error. So really strong performance on the search data set itself.
Okay, great on the small data set. But the real magic, the big aha moment, was transferring into ImageNet, right?
Absolutely. That was the main event.
Yeah.
They took those best cell architectures found on tiny CIFAR-10 and used them to build much larger NASNet models for ImageNet. That massive data set, 1.2 million images, 1,000 categories.
And they just trained the weights for these big networks from scratch using the cell structure found on CIFAR.
Exactly. And the results were, well, they were remarkable. This is where they hit state-of-the-art accuracy and showed surprising efficiency at the same time.
Tell me the numbers.
Okay, so their main model, NASNet, achieved 82.7% top 1 accuracy. That means it got the single most likely prediction correct almost 83% of the time, and 96.2% top 5 accuracy.
Which was state-of-the-art then.
Yes, among published results at the time. But here's the kicker. It wasn't just slightly better. It was a 1.2% absolute improvement in top 1 accuracy over the previous best human-invented architectures.
Wow, 1.2% is a solid jump at that level.
It is, but even more impressive. It did this while using 9 billion fewer floating point operations, or FLOPS. That's a 28% reduction in the computational cost compared to the previous best model it beat.
Get out. So it's more accurate and less computationally demanding. By a lot.
Exactly. That's the huge takeaway. They achieved higher accuracy with significantly less computation. They really break that common trade-off where you usually sacrifice efficiency for more accuracy, or vice versa.
So the AI didn't just find an accurate architecture, it found a fundamentally more efficient one. And they showed this wasn't a fluke, right? They had a whole family of these models.
Yes, they demonstrated that by varying the number of times they stacked the learned cells or changing the number of filters, they could create a family of NASNet models. And this family consistently outperformed the families of human-designed models across a whole range of computational budgets, from large to small.
That flexibility is key. It suggests the learned cell is a genuinely good building block. And this scaling worked even for really constrained environments like mobile phones.
It did. That was another really strong result. They specifically made a smaller NASNet version aimed at the kind of computational budget you'd have on a mobile device.
And how did that perform?
That smaller NASNet achieved 74.0% top 1 accuracy on ImageNet. What's striking is that this was 3.1% better than the previous state-of-the-art models that were specifically hand-designed by humans for mobile platforms, things like MobileNets or ShuffleNets, when compared at a similar computational cost.
Wow. So even on mobile, the AI design architecture beat the human-designed ones optimized for that exact scenario.
Yeah, it really showed that the design principles the AI learned were robust, scalable, and highly effective across different scales.
That's incredible. Breakthroughs at the high end, breakthroughs on mobile, all from the same core idea. And they didn't just stop at classifying images, did they? They tested if these learned features were good for other vision tasks.
Correct. That's a standard way to test how general and powerful the learned features are. Features learned by training on a huge classification dataset like ImageNet are often really useful as a starting point, a backbone for other computer vision tasks.
Like finding objects in an image detection.
Yeah, exactly. So they took their ImageNet pre-trained NASNet models and plugged them in as the feature extracting backbone for a popular object detection framework called Faster RCNN. Then they trained that whole system on the COSIO dataset, which is the standard benchmark for object detection.
Okay, so using NASNet features for finding bounding boxes around objects, what happened?
Another state-of-the-art result. Using the large NASNet backbone, the object detection system achieved 43.1% mean average precision, or MAP, on the COSIO test set.
And how did that compare?
That was a 4.0% absolute improvement over the previous best systems, which used sophisticated human-designed backbones like Inception ResNet v2. A really significant leap in object detection accuracy.
4% is huge in detection. And the mobile version?
Same story. The mobile-optimized NASNet backbone also led to big improvements in object detection, over 5.0% better MAT compared to using prior mobile-optimized backbones.
So it really confirms it. The features learned by these AI-designed architectures aren't just good for the original classification task. They're genuinely powerful, generic features that transfer really well to other complex vision problems like detection.
Absolutely. It's strong validation for the quality of the learner architecture.
Okay, so let's try to wrap our heads around this. This paper basically showed that an AI could learn to design its own neural network building blocks.
Right, these convolutional cells.
And it did this super efficiently by searching on a smaller data set, then transferring that learned structure. And the result, architectures that smashed state-of-the-art records on multiple big, complex vision tasks.
Yeah, beating the best human designs.
And often doing it with way less computational power needed.
That efficiency point is really key. More accurate and more efficient.
It's a really compelling demonstration of, well, machine learning automating a core part of machine learning design itself.
Exactly. Using ML to optimize the creation of the ML model structure.
So the big question then is, what does this really mean going forward? If machines can get this good at designing architectures for image recognition, arguably one of the most successful areas of AI, where else could this go?
It opens up a lot of possibilities, doesn't it?
Could we see AI-learned design principles transforming how we build AI for completely different fields? Language, maybe, robotics, or even outside AI and other complex engineering areas?
It certainly makes you think about that relationship between human intuition, human engineering skill, and what machines can learn to optimize or design. Are there limits to what an AI can architect effectively compared to what needs that, human spark?
Where does human creativity fit in when the AI is designing the blueprint? It's a fascinating question.
Definitely.
Something for you, our listeners, to mull over. What are the boundaries of machine design?